Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to be talking about zero-order reactions. So zero-order reactions are really one of the simplest ways we can look at a rate law. So this would be a reaction where A goes to B. But when we look at the rate, it will depend upon a rate constant, and the order of the reaction is zero, which means that the concentration doesn't actually play a role, because any concentration to the zero power is just going to equal 1. So the real notable thing about zero order rate reactions is they don't require upon the concentration of the reactants at all. And so they tend to proceed at a fairly constant rate. So this actually ends up being kind of fun when you look at it, because what we see is a steady decrease of the amount of our reactants. Because again, the rate is a constant value, and we see this constant decrease of our reactant concentrations. So one of the questions, and we'll dive into this a little bit later, is why would you have a reaction that's zero order? And usually the reason why is that the reaction rate doesn't actually depend so much upon the reactants as some other substance in the reaction. So this could be something like a metal surface, which can help accelerate the reaction, give a place for the reaction to occur. Also very common in biology is it's dependent upon the concentration of an enzyme, which is allowed to make the reaction proceed at a rate, or that there's some sort of reactant that we have a hard time including in our rates. Most commonly, this occurs with light. There are plenty of reactions that only occur if you have enough light to provide the energy to kickstart the reaction. So let's go ahead and talk about one example of these, and that would be the decomposition of nitrous oxide. So nitrous oxide can decompose into nitrogen and oxygen when put over a platinum surface. So in this case, what we're really seeing is the concentration, since it doesn't, of nitrate, since it doesn't, nitrous oxide, since it does not depend upon its own concentration, will just keep decreasing at a steady rate as the platinum chews it up. And as a consequence, we see steady production of both the nitrogen and the oxygen. And again, the reason why this reaction is zero order is because it's going to be this availability of the platinum surface. Since the reaction can only occur on the platinum surface, there's only so much surface for the reaction to take place on. And this is really what will control the speed. And so again, the rate law for this reaction, we're going to see a steady decrease with respect to the nitrous oxide. But note here that because of the stoichiometry, we have to bring in this 1/2 term. Again, negative because the nitrous oxide is decreasing. The half to go ahead and represent that we have one reaction taking place for every 2 moles of the nitrous oxide. So do keep in mind, if we're dealing with systems that don't have stoichiometry, whenever you're dealing with systems that have stoichiometry, that you really should be including these extra 1/2, 1/3 to represent how much of the reactant is being consumed. So let's go ahead and deal with another zero order reaction. And this is the oxidation of ethanol in your body. So when your body has ethanol, this is pretty much a toxic substance. And so your body's going to try and get rid of it with alcohol dehydrogenase. And again, we'll oxidize the system with the oxidizing agent of NAD+. So this will go ahead and pull off essentially a hydride, so H-, and an extra proton. So one of the things that's really fun about this reaction is that it's actually going to be the concentration of the enzyme that controls the reaction, and not the NAD or ethanol. And so as a result, what you tend to see is this steady decrease in the amount of ethanol until you get to really low concentrations. So for the most part, we see ethanol as having a zero order dependence. And so as a result, using this simple rate law, looking at we have that the decrease in the amount of ethanol present over time is related to just the rate constant. And so once we know that the rate constant, we can go ahead and predict the exact change in the amount of ethanol over any time interval, which is very important if you want to know how long you're going to stay drunk. And it has a lot to do with an individual body system. So this exact rate constant can change from person to person. Now, one of the things we can do is we can go ahead and start with this basic rate equation and try and switch it back from infinitesimal changes. So again, looking at just the slope at a single point, to essentially discrete changes by taking the integral of both sides. So more or less undoing that first derivative. And this will actually be fairly simple for the zero order case. So for example, I want to go ahead and determine what will be the change in concentration if I go from time 0 to essentially this approximately 1 hour point. And that can essentially be done by integrating the system or finding the area under the curve, figuring an exact amount of change of the ethanol for a given point in time. So for that, we're going to integrate the system. And so we'll integrate the right side, the left-hand side from with respect to time from 0 to whatever time I care about. And we'll go ahead and integrate the concentration of the ethanol from 0 to whatever time we care about. So don't need to know the details of an integral. The important thing is that it kicks out a fun function. It will be more or less the rate constant times the change in time, which in this case is t, will be equal to the negative change in the concentration. So the negative of the concentration at time t plus the concentration of the initial ethanol. So we can go ahead and rearrange this. And now we can go ahead and solve for the ethanol concentration at any given time, as long as we know the initial concentration and that rate constant. And so this form is referred to as an integrated rate law because we took our rates and we integrated it. Yes, we're ever so clever. And it's worth noting that this basic form will hold for any zero order reaction. Only special nuance is taking into account for the stoichiometry, and that can be done with this K term. If I've got a 2-to-1 stoichiometry, I would need to effectively double the rate constant. Otherwise, if you know a reaction is zero order, initial concentration, final concentration, rate constant, and you have it. However, another useful way to useful metric for a zero order reaction is going to be the half-life, or simply what amount of time will it take for half of the reactant to be consumed. So for me to consume half of A as I go to B. We can do this using our integrated rate law and simply solving for at what time is my concentration half of its initial value. So I plug in half A naught for my initial time, and I just concentration. I go ahead and call this ending time as my half-life. So what we can do is go ahead and rearrange this. We can subtract A naught from both sides. So now we have negative KT equals negative 1/2 of our initial concentration. Divide both sides by negative KT, and I should have a concentration of A naught over 2K. Apologize for the typo there. So what we find here, and this is the important point, is the half-life for any zero order reaction only depends upon the initial concentration and the rate of the reaction. And this actually has some fun consequences. So what we're going to see is that our half-life will change with respect to time. So my initial half-life will not be the same as my half-life at other points. Because one of the things that happens is since the rate of reaction doesn't end up changing, it's going to take less and less time to consume half of those reactants. So for example, my initial half-life for this ethanol oxidation reaction will take a little over an hour. But the second half-life takes closer to a half an hour, and then like 20 minutes. And each time the half-life will go further and further down. Till at the very end, the half-life is pretty much infinitesimally short. And this is an important feature to note about zero-order reactions. The rate of reaction is constant. That means that when you're figuring out how much time it takes to consume the species, this has a greater proportion of the concentration as we go on with time. So next time, we're going to go ahead and look at first-order reactions. Until then, take care.